All right, so this is part 2 of what I was talking about with those eigenvalues and eigenvectors. And again, I just want to make sure I'm clear on what I meant by choosing a value here for this eigenvector. The straight line solution that we got was y equals -1/2 x. So when you write that eigenvector, choose a value for x that gives you nice numbers. I don't want that fraction. Like had I chose x equals 1, for example, then I would have had 1 for the x, and then I would have had -1/2 for the y by plugging it in. But instead I chose 2. So if I chose x equals 2, plug that in, the corresponding y value is -1. Either is acceptable, just pick the one that's easiest. So my corresponding eigenvector, I'm going to go with 2, -1. Anything along that line, though, would be acceptable. So part C said to go ahead and write out the general solution to this system of differential equations. So we're going to have my general solution, here it is, it's going to be K1 e to the lambda, which was 4t, I believe, right? That was my first, let me go back, my first lambda value was 4. So it's going to be K1 e to the 4t times the corresponding eigenvector that was 1, 1. And then the other solution is going to be K2 times e to the lambda for that, which was 1, don't forget. So that's just t times the corresponding eigenvector for that one, which was 2, -1. And that's going to be our general solution based on those eigenvectors. All right, the last part of the question said to sketch the vector field and verify what we have. So let's go ahead and do that. I'm going to pull up I think Desmos is what I use. So let me pause the video real quick. Let me pull up Desmos and see what this looks like. Okay, so I've got this pulled up in GeoGebra actually, and I've put the link in OneNote so you can see later where this is. But let me just kind of show you how we're going to put this in. Let me see if I can make this window a little bit bigger. Here we go. The window's a little bigger. So when you put this in, you're going to put in the dx dt and the dy dt that you started with. So you'll notice that, let me go back real quick, the original system that they gave us in matrix form, it was this 2, 2, 1, 3. So think about if we wrote that out, that would be equivalent to saying, let me hold on, I don't want to clutter this up too much. That would be equivalent to saying dx dt is equal to 2x plus 2y, and dy dt is equal to x plus 3y. So there's the component form of that system. That's what you're going to put in for your vector field. So let's go back. Let me go back to GeoGebra. So for the x component, I'm going to put in 2x plus 2y. And then the y component, I'm going to put in, I already forgot what it was. It was x plus 3y. And hit enter, and that's going to give you your vector field. And it's a little hard to see what's going on, and I encourage you to go to the link I posted in OneNote and play around with some of these different options. So these x and y's affect the density, basically. How many vectors in each direction do you want them to plot? This affects the length. How long do you want to make those vectors on the actual sketch itself? So play around with these numbers just a little bit, and I think this affects the arrows themselves. Yeah. So what I'm going to do, let me go ahead and screenshot this, and I'm going to put this into the notes. Let me go. All right, let me go back to the notes here. I'm going to put. Let me see if I can cut and paste. All right, so that's what we just had. That was the vector field, and I think it's a little bit hard to see exactly what's happening. But the idea is we've got these two straight line solutions that help us, because we can get those eigenvalues that help us get that general solution. So remember what we had highlighted. We had y equals x and y equals -1/2 x. So y equals x, of course, would just be the line going through the origin. just like this. And then the other was negative, what did I say, negative 1/2 x. So that would be the line that looks like this. And the slope, or I'm sorry, the direction, let me try it again. The vector field gives us the direction that these are going in. So the direction field, or the vector field, I'll get it right. The vector field gives us the directions that each of these little segments are going. So they're telling us about the behavior in terms of, are they going away from the origin, towards the origin? And we'll talk a little more later about what all that means. But you can see in both of these, they're going away from the origin. Now I paused the video and I pulled up, let me find it. I did also graph the phase portrait. And remember, the phase portrait is just the slope field basically for a system of differential equations. And in a way, I actually think it's a little easier to see what's going on with the phase plane, or the phase portrait. Let me show that to you real quick. Same system here. And what we've got is, we've got same thing, basically. This difference between this and the vector field is this doesn't show you the arrows, so it doesn't give you the directions, the magnitudes. These points are a little bit more generic, or the little segments rather, a little more generic in terms of not giving you the direction and the magnitude, but they do give you the, you can see basically the behavior of what's happening. And I wanted you to just kind of see, I think it's a little easier actually to see those straight line solutions. So you can see there is a general solution, or a solution rather, that goes through y equals x. And then we have this other one that went through y equals negative 1/2 x. We'll play around with these and we'll get more and more into what the vector field tells us as we go through these. But for right now, what I want you to just kind of focus on is how we get those eigenvalues and how we put those together to get a general eigenvector that can be used to write the general solution. Because this is a really powerful way of solving these systems of differential equations. All right, so we'll do some more practice and I'll see you guys in class.